Okay, great. So everyone, welcome to our second GROOT talk of this week. Today we'll be hearing from Dezhou Li about the Cartan-Leray spectral sequence of the braid group.
Yeah, thanks. Thanks for the invitation. So I'm gonna divide my talk into 5 parts. The first part is the definition. Second part is the purpose of my ongoing research. Third part is the general strategy. And the fourth part is some background knowledge. And the last part, I'm gonna mention some of my current progress. So let's start with some definitions. The configuration space of k-order points in a topological space X is defined to be K of X. It's just a set of k points in Xk such that whenever whenever I is not equal to j, we have xi is not equal to xj. And this equips with a subspace topology of x to the k. And we can observe that we have a natural sigma k action on this space by just simply promoting the points. And this sigma k, if you don't like it, is just a symmetry group on k points. Okay, so we can also define the unordered configuration space is just the quotient space bk of x to be defined as k of x divided by sigma k. And we can denote that bk of x to be the string union of bk of x for k greater and equal to 0. Okay, let's start with some easy examples. So if k is 1, the k of 1 of x is just this condition here is trivial. So this is just x. So this is boring. However, when k is 2, x is Rn, we have that com2 of Rn. So what is this? We can show that this is actually homotopic to S n minus 1. So we send, so what is this map? We send 2 points x1, x2 to x2 minus x1 divided by its length. Okay, so this is just simply the Gauss map. Okay, okay, that's ordered configuration space on 2 points. What about the unordered case? We can observe that we have a sigma 2 equivariant. So what I'm saying is that we have a sigma 2 action on both sides, and this map, this sigma 2 action actually is equivariant. So we can show that B2 of Rn is actually homotopic to the Rp n minus 1, the real projected space of the dimension n minus 1. Okay, so that's 2 easy examples. Okay, so the final purpose of my research is I'm gonna to do something regarding to the cohomology of the unordered configuration space of a planar graph. So let gamma to be a planar graph. The general question to ask is H star be gamma with coefficient of z torsion free? Okay, so that's a pretty broad questions. And one way to approach this question is to study what happened when we have a planar graph be embedded into R2, and this induced a map at the level of configuration space. By pulling back, we have an induced map F star of H star of B of R. Sorry, this should be R2 here. So R2 and the H star of B of R2 to H star of B of gamma. Okay, and we know that by Cohen, by people from before, that we know that we have a torsion elements in here. So alpha is torsion. What happened to F star of alpha. Is this a torsion element for H star B gamma, or is it just simply 0? So that's the final or the stage 2 of my thesis. Okay. Okay. Do we have any question regarding to the definition and the purpose of my research? Okay. So this simply divides my question into 2 parts. The number 1 part is I want to study the cohomology of configuration space of Rn. That's the first part. Then I'm gonna restrict attention to n is equal to 2. Then study the cohomology of configuration space over a planar graph. And for this talk, I'm gonna focus on the first part of my research. Okay, and I'm only interested in x is equal to Rn for this talk. So I'm gonna denote comp k to be comp k of Rn and the bk to be bk of Rn. So I'm gonna simply just now writing those 2 parts. Okay, so I want to do research. So I want to do research. I want some tools to my in my hand. I'm gonna use, so most of the part I'm gonna use 3 main tools. The number 1 is the Cartan-Leray spectral sequence. So if X is the free G space for a group G, then there is a spectral sequence of the form where E2 page is isomorphic to HS of G with coefficient of HT of X. And this converges to the cohomology of X mod G. And for our purpose, we let G to be sigma K, and we let X to be comp K. Okay, so the most important theorem I'm going to use is the Cartan-Leray spectral sequence. And the second tool I will be keep using is the map between 2 spectral sequence. So I'm going to use the words map out to mean that we have a map comp K to comp K1 times comp K2 times all the way to comp KL, such that the summation of those small Ki is equal to K. And this map P is just the projection map. So let me do a concrete example for how to construct a map between 2 spectral sequence. If we only do that, we have A plus B is equal to K. We can observe that this map is simply sigma A times sigma B equivariant. Okay, then this induces the map at the level of cohomology of a map HT of comp A times comp B to comp T of HT of comp K, and this induced map is a sigma A times sigma B homomorphism. Okay, but in the end I want a sigma K homomorphism. How do I do that? So I just apply the universal property of the.
How exactly this map is a projection?
Oh, so why this map is a projection?
Yes.
Okay, so I'm gonna say something. Okay, so if I have a point x1, x2, all the way to xa, then I have a xa plus 1 all the way to x b, I think a plus b plus 1, I guess. So I simply send the point, so it should be x sub a plus b, because a plus b is equal to k. So I have a k point here in comp k, and I send the first a points to comp a, and I send the last b points to comp b. So this is in com A, this is in com B. So when I say projection map, I actually mean this. And yeah, so I guess, yeah. So I have a question from the chat. Why we need F to be sigma A times sigma B equivariant? Because in the end, you want to build so why do we need that? Okay. So in the end, I want to build a map between two spectral sequences, especially I want that map to be a sigma K homomorphism. So this sigma A times sigma B equivariant gonna later, so you will see later. Okay, so I have a F star, which is sigma A times sigma B a homomorphism map, and this will induce the map from induction of sigma A times sigma B to sigma K of HT of com A times com B to HT of com K. And this map is a sigma K homomorphism. Okay, because we can actually embed the sigma A times sigma B as a subgroup of sigma K. Okay, so we build a sigma K homomorphism by applying the cohomology functor again in the front. We have a new F star, which is H of S of sigma K with the coefficient of induction, sigma K, sigma A times sigma B, HT of com A times com B to HS of sigma K, HT of com B, com K. So this is the a map between two spectral sequence. We can simplify the input a little bit by the Shapiro's lemma. We get that this is isomorphic to HS of sigma A times sigma B with coefficient of HT of com A to com B. Okay. So if your input map is not a sigma A times sigma B equivariant, we cannot build a map between two spectral sequences. Which gonna commute with our differentials in the spectral sequence. So that's okay, that's out of topic, but I'm gonna mention that if I'm gonna consider a map in under these circumstances, if I have a map going this way, we can build a map, but this map is not gonna be sigma A times sigma B equivariant because by definition of being configuration space. And this induced map between two spectral sequences actually is wrong because it's not the sigma A times sigma B equivariant to begin with. Okay, the last tool I will be using is a tool to study. So here, okay, I probably know this, I probably know this, but do I have description for HT of com K? Okay, so I do have a tool to describe HT of com K using some geometric way. So it's convenient to work with homology basis. Given a tree or even more generally a forest, we can construct a submanifold of com K. So for example, in com7, I have a forest with the first tree 3 leaves, this one. And I have a second tree with 2 leaves. The third one, 1 leaves, and the last one, 1 leaf. And we can build a submanifold of com7 by doing this planetary system. So I have a x2 here, and I have x3 here, x1 here. And for the second tree, I can build a planetary system x1 here, x2 here, and x1, x1. Okay, if I modify the index a little bit, I call this x4, I call this x5. I have x6, x7 here. And we realize that by together, this is a point in COM7. Because as you can see that the x1 is not equal to x2, x1 is not equal to x3, and whenever I is not equal to j, that xi is not equal to xj. So this certainly satisfies the definition for being a confusion space. Okay, so I'm picking those trees specifically, and those kind of trees called a tall tree. So a tree like this, by putting the smallest number at the deepest leaf, is called a tall tree. And a tall forest is a disjoint union of tall trees. So here, as you can see, 1 is the deepest leaf for my first tree here, and is of course, is the smallest number among 1, 2, and 3. And also, I have a 1 here, 1 here, and 1 here. So a tree like this, like 2, 3, and 1, is a binary tree, but it is not a tall tree. So why do I need this definition of tall tree? So if I let m sub k1, k2, all the way to kr be a sigma k submodule of h star of comp k spanned by tall trees, tall forest, of K1, K2, and the KR leaves, such that the summation is equal to K. So for this example here, I'm actually looking at the submodule of the form m sub 3, 2, 1, 1. Okay. So why am I creating this new stuff? Because by a theorem by Cohen, that we can use this to describe the homology of configuration space of K points. So this H star of comp K is isomorphic to direct sum of blocks from 1 blocks to K blocks, direct sum of comp1 plus K1 plus K2 plus all the way to KR is equal to K, with M sub K1, K2, and K sub KR. So we can approach the H star of comp K using this module M sub case. Okay. So, okay, then you are saying, okay, so in order to study this, you somehow create something that seems not too easy to be analyzed. Is there a way to actually interpret this one more step? Yes. Okay, so if we go back to this example here, we observe that the first, so if I'm observing this diagram here, this is actually in comp 3, right? This is actually in comp 2. This is in comp 1. So this is in comp 1. So we can somehow decompose this module using smaller module. So what do I mean by that? So proposition M sub K1 all the way to Kr is the induction from the product of sigma L raised sigma Ki's to sigma K, where L is the number of times, where Ki appears for the tensor product, of the top homology of comp Ki's. Okay, so for our example here, this M sub 3 2 1 1 is actually isomorphic to induction of sigma 3 times sigma 2 times sigma 2 raised sigma 1 to sigma 7 for the tensor product of M3 times M2 times M1 twice. So what is M3, M2? M3 and M2 are the top homology of configuration space of J points. Okay. So people may ask, what is this raised product? So this raised product is by definition, this is just so if I have a sigma L raised sigma K, so this by definition is just sigma L semi-derived product of sigma K L times. So not only we have a sigma K action on the configuration space of K points, we also have a sigma L action to permute those L blocks among them. So we have 2 actions going on here. Okay, so right now with all the tools I have, so I have a Cartan-Leray spectral sequence right here, and I have the map between 2 spectral sequence right here, and last but not the least, I have the description of the homology or cohomology of configuration space. Okay, then I can actually do some work here. But before doing that, let me tell you the background knowledge. So for K equal to P, Cohen used the Cartan-Leray spectral sequence to compute the cohomology of BP of Rn with coefficient of Fp. with the help of vanishing, invariant, and porosity theorem. So here, K is equal to P with coefficient of Fp. So the coefficient here is not the integer Z, is the field. Okay. So what is vanishing theorem? So vanishing theorem essentially is that we have Hn of G with coefficient of a module M is 0 if G, the order of G is invertible in M, and N is greater than 0. Okay, so by the vanishing theorem, we can describe the E2 page of the Cartan-Leray spectral sequence, which only contains 2 non-vanishing rows, only in 2 rows. So this row corresponds to Hs of sigma p with coefficient of Fp. And this row corresponds to Hs of sigma p with coefficient of MP. Don't forget that MP is top homology or top cohomology of the configuration space of P point in this case. And because we are working over a field, we don't tell the difference between homology or cohomology at this time. Okay, and but I still have something I need to figure out, which is when S is 0. So I have a T equals 0 and the P minus 1 and minus 1. Okay. So by the vanishing theorem, this is my E2 page. And by invariant theorem, so by invariant theorem, we know exactly what happens to S equal to 0. So when so this is all gone. So by invariant theorem, that if n is odd, so if n is odd, we only have something non-trivial when t is 0. If n is even, I have something sitting here for t equals n minus 1. Okay. So by the invariant theorem, I have a modified version of E2 page. Okay. And lastly, I have the porosity theorem. So what is porosity theorem? Porosity theorem says that if, so let me write here. So porosity theorem says that Hs of sigma p with coefficient n is actually isomorphic to Hs or H to the power of S plus 2 times p minus 1 of sigma p with coefficient n for S greater than 0. Okay, so why is this useful? Okay, so we know that in the end, I want to compute the homology or cohomology of BP of Rn, right? And we know that this is a manifold of dimension n times p. So we know that cohomology of this object here should be trivial if the degree is greater than n times p, right? And if we observe the E2 page here, we know that for large degree, the only things can make the final page to be 0 is that for large degree, this differential here, if I call this dr, must be an isomorphism. Okay, by the porosity theorem, we can actually push this isomorphism to a small degree. So by isomorphism, we can push things to the left, says that, okay, this is also an isomorphism. This is also an isomorphism. and so on. So I can draw the final page of this object. So, okay, so this is infinity page. By the shape of the differential, we can see that this row is gone, right? And we have something left for us, which is just this chopped up version here. So I have something here, and I have depends on n is even or not. So I have something happen here. Okay. So we have a description of H star BP of Rn. Okay. So do we have any questions so far? So do you need some restriction on the ambient manifold to build a map other way? Sorry, I'm not following the question.
That one looks like it was from a little while ago,
Yeah,
about 10 minutes.
it was the mapping. Okay. So simply, if I want to build a map between two spectral sequence, okay, where is it? If I want to build a map between two spectral sequence, okay, I need an equivariant condition to begin with. Of course, I can build this. I can build a map, but this map is not gonna be the equivariant map. If it is not an equivariant map, then the map between two spectral sequences should not be the real map between two spectral sequences. However, you can override that part by considering the opera, but that's not the part of the discussion I want to talk about here. Okay. Okay, so I'm gonna keep repeating. I'm gonna keep using the same technique to approach other cases when k is greater than p. I'm gonna keep using Cartan-Leray spectral sequence. I'm gonna keep using the map between spectral sequence. Okay. So I'm gonna divide the problem into some cases. I have a k greater than p and less than 2p for my first case, and I have a k equal 2p for my second case, and the k greater than 2p less than 2p squared, and k equals 2p squared. Then in the end, I can make some general statements regarding to those two interesting cases. So why are they interesting? And we shall see in a second. Okay, so for p greater than for k greater than p less than 2p, and this divides into two smaller cases. When k is equal to p plus 1, we can use a map out by saying that, okay, comp p plus 1 to comp p. By observing the map between those two spectral sequences, we can actually compute that there is nothing new for this case. So H star BP is actually isomorphic to H star BP plus 1. Okay, and for k greater than p plus 1 less than 2p, we can draw the E2 page or spectral sequence. So let me draw the spectral sequence for E2 page. So for if n is odd, we have two non-vanishing rows as the old case. So those two rows corresponds to m sub p 1 1. Here I'm picking I'm picking k equals p plus 2 here. And this bottom row corresponds to m sub 1, 1, 1, 1, where the summation of those 1 is equal to p plus 2 when n is odd. And when n is even, on top of that, we have 2 more non-vanishing rows sitting on the top. So I have 2 more non-vanishing rows sitting on the top, and this top row corresponds to m sub p2, and this bottom row corresponds to m sub 2 1, 1, 1. Okay, then we can use the map out from com p plus 2 to com p times com 2 to show that the differentials between 2 closed rows are trivial. So they are trivial maps. And we can show that the next step, the differential between those 2 rows are also trivial. And we can show that the next step is the map between those 2 rows and those 2 rows. We can show that they are isomorphic to each other. So the infinite page of the spectral sequence looks like the old one, but we just have another copy sitting on the top. So we have a so we have a 0 here and a minus 1 here. So this is the infinite page of com p plus 2 to com to b p 2. Okay, and other cases during this range should have the same infinite page. Okay, so I'm gonna talk about what happened when k is equal to 2p. This shall be an interesting case because a new class, a new homology class or new cohomology class should rise at this case. Okay, so allow me using the same technique to draw the E2 page of this spectral sequence. When n is odd, I have, you may guess, I have 3 non-vanishing rows. And they are related to MPP, MP111, where the summation of those 1 is equal to P, and the last row corresponds to M sub 111. Okay, this is when n is odd, and as you will see that odd case is always boring. We want to look at the even case. When n is even, on top of that, we have 3 more non-vanishing rows sitting on the top. Okay, it get a little bit messy. Okay, so this row corresponds to m sub 2p, and this row corresponds to m sub p2 111. Direct sum another non-vanishing parts, which is m sub 2222. The summation of those 2 is equal to 2p. And this row corresponds to m sub 2 111. Okay. So I'm going to look at the differentials between those 3 rows. So look at those 3 rows. So if I call that this is D1, if I call this is D2, I can show that D1 is injective with the image isomorphic to the part M sub 222. And I can show that D2 is surjective with the kernel isomorphic to M sub 222. So for some range that the map between those three rows actually forming an exact sequence. Okay. And of course, the same technique as before, that we can show that those three rows are forming an exact sequence. But I'm gonna focus on the this row here because we have this this bad guy here, okay, M sub 2222. So what happened when the starting point of D1 is 0? So if we are looking at the second quadrant, the starting point of D1 is at the second quadrant, then we only have the map from here to here. So we only have D2, right? And we don't have D1 coming out of this spectral sequence, coming into the spectral sequence. So for small range, for small total degree, we're gonna left with the kernel of D2 is this part. So what is this part? We can compute that this is correspond to H star of sigma 2p with coefficient of M sub 222. Okay, by the proposition I have, I can understand this using the induction. So this is induction of sigma p raised sigma 2 to sigma 2p with M2 tensor p times by the proposition I have probably a long time ago. You may already forget, but that's all right. Okay, then by the Shapur's lemma, so the Shapur's lemma, so this is the proposition I had before. By Shapur's lemma, this is isomorphic to sigma p raised sigma 2 with coefficient of M2 tensor p times. Okay, how do I approach this? By the Hausdorff serial spectral sequence, I can decompose this one more step. This is isomorphic to H star of BP M2 invariant sigma 2 tensor p times. Okay. And what is M2 sigma 2? So M2 sigma 2 is just the top homology or top cohomology of n-1 of Rp n-1. So if you recall that I mentioned this example a long time ago, so this is just the ground field with grading n-1. Okay, so and you can see that this sigma p acts on this by permuting the factors. And for each factor we are permuting here, we actually add a -1 sign in the front. So this is actually isomorphic to H star of sigma p with the sign representation. Okay, so what is this? So by May, H star of sigma p with the sign representation as the coefficient has an additive basis. Of the form beta v to the power of epsilon, beta v to the power of s, and the beta epsilon v prime. Okay, so beta here corresponds to the Boxton homomorphism. So beta is the Boxton homomorphism. And S here is greater and equal to 0, epsilon here is either 0 or 1. And the V here is a class of a degree 2 times P minus 1 minus 1. And the V prime here is a class of degree P minus 2. So for here, if n is equal to 2, we can draw the infinite page of this spectral sequence we have something at the bottom. It's a chopped out version as before. This corresponds to t equals 0. This corresponds to t equals n minus 1. And here we have something more because D2 is surjective with kernel equal to this part. So this is just correspond to t equals p times n minus 1. Okay, when n is 2, we have v prime and beta v prime. So we can modify this one more step by saying that this rule only contains 2 non-trivial entries, and they are v prime and beta v prime here. Okay, and those two will give us a new class towards the cohomology of B 2P of R2 with coefficient of FP. Okay, I guess I'm almost out of time. Yeah, that's pretty much my talk. So the next interesting case happens at k equals 2p squared, where there will be a new cohomology class arise, which is related to the cohomology of sigma p squared with the coefficient of the sign representation. Okay. And for k equals 2p cube, you may guess that this related to h star of sigma p cube of fp with sign representation, and so on. So that's how far I have done so far. And thanks for, yeah.
Oh, great. All right, so let's thank the speaker for a wonderful talk. Feel free to unmute yourself and clap, or use the clap emoji in Zoom. So thanks. And right, does anyone have any questions?
Yeah, the Cohen is the Fred Cohen. It's not the Raffle Cohen. We have a lot of Cohens here. I think he just passed away like 3 years ago or 2 years ago. Fred Cohen. Yeah, he laid the foundation for this configuration space topic.
I have a question.
Yep.
So in the last string of isomorphisms, just above this spectral sequence, could you just repeat how did you go from the wreath product? So at the break of the line, basically, the isomorphism.
From here to here.
No, the next one. From
So
the wreath product to the sigma
from
phi.
here to here.
Yeah, yeah.
Okay. So this is related to the Langton-Hauschild-Serre spectral sequence. So this is related to that. So if we have a group extension of the form, for example, you have a group extension of, so for this example, I have a sigma p, sorry, 1 second. So I have a sigma, so I have a sigma p raise sigma 2 in the middle. And I have sigma 2. Yeah, well, I have a sigma 2 times P here, and last one correspond to sigma P to 0. So if I have a group extension of this form, or more generally, I have a subgroup H embedded in G with the quotient G mod H, I can construct a spectral sequence of the form that E2 page is isomorphic to H S of G mod H with coefficient of HT of H. And this spectral sequence converges to the things in the middle. Okay. So here, because sigma 2 here is actually co-prime to our ground field FP. So okay, I guess I need to do this step by step. So how do I do this?
I think I've for me it's enough. But I don't mind if you repeat the whole step. But I also want to give you the choice to stop here if you want. I'm happy with the answer. Thanks.
Okay, so I'm using this technique to say that this spectral sequence collapse at the E2 page. So I have this.
Yeah. Okay. Okay. Thanks a lot.
Great. Yeah. So any further questions? Looks like there are no more in the chat. So yeah, with that, let's go ahead and thank the speaker once more then. So
yeah, thanks for the opportunity.